Hello guys, welcome back to quantum control lectures, and we would continue with our introduction of basic quantum mechanics. And in this lecture I would start with the statement of postulate 2 of quantum mechanics. So the statement goes as follows. It says to each dynamical variable which is a physical concept like momentum energy, temperature, etc. There corresponds a Hermitian operator, uh, which is and the possible values of dynamical variables are eigenvalues of the operator. So what it is essentially saying that any dynamical variable like momentum, energy, temperature, we model these variables or physical concepts by a Hermitian operators, and the all the eigenvalues of these Hermitian operators are the possible values of this dynamical variable. So why we have chosen them to be Hermitian? Because we know the eigenvalues of Hermitian operators are real. So that it corresponds to reality, because in reality when we measure these quantities or dynamical variables like energy, pressure, we don't observe complex valued measurement. We always get real numbers. So that is the reason of choosing Hermitian operator to model them. For example, and very important example, is the operator corresponding to the total energy in quantum mechanics, which is denoted by this H, and this hat says that there is an operator, not an symbol or a variable, which is nothing but the kinetic energy part plus the potential energy part. And note, these are operators themselves. This is momentum squared operator, and this is position coordinate of this is an operator corresponding to the position of the particle, and V is a function which denotes the potential energy. So this is Ke, kinetic energy, and this is Pe, and this sum is the total energy, and it is called Hamiltonian. Now that we know what is a state of quantum system and the dynamical variable associated with it, and how they are modeled by vectors in Hilbert space and Hermitian operators operating on them respectively. So I want to clarify one thing about the physical states, that is any state psi are same up to a global phase, that is this state and some state having a global phase are equivalent. Why? Because a global phase does not change the expectation value of any observable. Then I have to define to you what is an expected value of an operator or a dynamical variable in quantum mechanics is, if we assume the system is in the state psi and it is normalized, then the operator, any operator O, whose expectation value would be given as, if you remember or recall that any operator, first you have to understand that any operator corresponds to dynamical variable, and expectation value of any random dynamical variable is if that variable is O, then this expectation value is denoted by surrounding this variable O with this kind of angle brackets, and it is given by as if the random variable takes this value lambda 1 and times the probability that this random variable takes this value lambda 1 plus the random variable takes this value lambda 2 times the probability that this random variable takes this value lambda 2 and so on. So this could be written as summation over index I lambda I probability that this random variable takes this value lambda I. Now in quantum mechanics, if you remember, I have told you that the probability is given by the magnitude square of probability amplitude, which is if I say that the eigenstate corresponding to this eigenvalue lambda I of the operator O is I, then this probability is given by the probability amplitude. This is the probability amplitude and its square would give me this probability. So this would be this. This is complex conjugate of this quantity, and you know that if I multiply to any complex number its complex conjugate, I would get its magnitude square, and this is equal to the probability that the random variable which corresponds to this operator O takes this value lambda I. Okay, so this is how the probability is rewritten. Since this all three of these are complex numbers, then I can rearrange them without thinking of any commutation relations because they always commute. I can write them as such. This again, this lambda I, it can be written as this because this operator when applied to this eigenvector would give me lambda I. That's how an eigenvector is defined, and when then if I apply this bra on it and assuming this set of eigenvectors are normalized, then it would give me lambda I because the inner product between I and I would be 1. So and if you notice this part, and so this is again both of them are completeness relation which sum to the identity operator along with this summation operator. So this would be identity operator, and any identity operator multiplied to any other operator give back the same operator. So this would be O again. So this is how the expectation value of any operator O would be given in quantum mechanics, understood as the expectation value of an dynamical variable in quantum system when the quantum system is in the state xi. So this is how we define the expectation value. And coming back, the continuing my point that any state up to a global phase is equivalent to each other. So if I call this scaled state as phi, then the expectation value of any dynamical variable and its corresponding Hermitian operator, then its expectation value in that state, that this operator would be given by this, as we have done over here. It is same as times e to the power minus iota theta xi. If I club both of them, it would give me 1, and again I would get this, which is the expectation value of the operator O in the state xi. So you see, then a vector xi or alpha xi, alpha times, where alpha is any scalar taken from the set of complex numbers and alpha is not 0, represent the same physical state. So for this reason it is often more appropriate to speak about rays of direction in Hilbert space H as representing the state of the system. We can now move on to the postulate 3 of quantum mechanics, which its statement goes again as follows. The state of a closed system evolves in time, described by unitary transformation. Or operator. This is how a closed system evolves in time. There are two important words that we have assumed. We assume that the system is closed. By closed, we mean that the system or quantum system is completely isolated or closed from the rest of the system. So we will discuss later what will happen if we relax this assumption a bit, that is, system is open. So any closed system, as we have talked earlier, obeys Schrodinger equation as its evolution equation. They wish to investigate that whether it is possible to obtain an operator which, when applied to a vector at particular time, gives out a vector at an specified future time. That is, if we are looking for the existence of this kind of an operator, unitary operator like this, which when applied to some initial state xi of 0 gives me this vector of xi of t in any future time t. So let's see what kind of form it takes, this u operator, if my system xi is a closed one and obeys the Schrodinger equation. Okay, so this u will take a special form. It's not necessary that u takes this form always, because we have assumed that this system is closed. If it is open or any other case, this u won't take the special form that we are gonna evaluate shortly. So this is how we defined the Schrodinger equation. Okay, and if we substitute this LHS xi of 0 so this would become an equation involving u only if we note that both this thing cancels in a sense. Okay, so this is what this equation become, and if you solve this equation, the operator takes this form. Okay, So this is what my unitary this evolution operator takes if my system is closed. So if I take this complex conjugate, this would become iota h hat t by h. This would become, sorry, plus. So if you note that u dagger is a unitary operator. So with this, indeed its evolution operator is unitary if my system is closed. So I want to give you some physical significance of these above two discussion of the invariability of quantum states if we scale any state by a global phase, and the special form the evolution operator takes when the system is closed. Okay, so the physical significance is that the exact value of ground state of a system is not important. That is, ground state is that state whose corresponding energy is the lowest possible for that system. Okay, and the other state whose energy is higher than this is measured in relative to this ground state energy. Okay, so this is the lowest possible energy state, the state, and it is called ground state energy of the system. So the exact and absolute value of the ground state energy is not important, and that is if we have a total in energy operator h hat or the Hamiltonian as h hat, then if I shift the Hamiltonian by a constant c, a constant or a constant shift in Hamiltonian, then the my evolution equation would give me this as an evolution operator applied on the initial state xi or 0. Again, this thing we can take out, and if you notice, this is nothing but a global phase, and we can neglect the and it is same as xi of 0. That is, the evolution behaves as if there was no constant shift introduced in the system. Okay, so evolution doesn't care, the time evolution doesn't care whether there was any shift in the Hamiltonian or any shift in the constant shift in the measurement of energy. Okay, only therefore the exact value of the ground state energy is not required. Okay, only relative, because any energy corresponding to any other state which is higher than this ground state energy would be measured relative to the ground state energy. So, and another thing is that is what does the unitary evolution means for a state. By that I mean, suppose if you at t equal to 0 the state was in xi of 0 and it is normalized, that is xi of 0 inner product is 1, then xi of t times the unitary operator xi of 0 is given, this xi of t is given by this, and if I take the inner product of xi t with itself, then it would be xi of 0 u dagger u xi of 0, and you know this is the identity operator xi of 0 xi this would be 1. So this means that unitary evolution preserve the norm or the length of the states, which are represented as vector in Hilbert's space. So before moving to the next postulate, I want to introduce the quantum physics of angular momentum, which is very important for the control of qubit systems or two level systems. Okay, so before that, I want to introduce you to the special kind of form that the operator corresponding to the momentum variable takes. Okay, consider a particle, that is a particle moving in a space where there is no force or influence. So it means there is no potential in that space. So my Schrodinger equation becomes del square xi x and t, because our wave function can be a function of both space and time. Let us guess the wave function would have a spatial part and a temporal part. We can bifurcate this Schrodinger equation, and it is equal to the time independent Schrodinger equation, which is given like this. And if you note, the double derivative of the spatial part would give me a number, this a twice, times xi of x minus a square by 2m equal to e times xi of x. This would give me a squared as 2m e by h bar squared. And you know, if my particle is moving in a free space, then its potential energy would be 0 and the total energy would be given by the kinetic energy it possesses. So E would be equal to the only the kinetic energy, which you know is given by p squared by 2m by h bar squared, with 2m to m cancelling, p squared by h bar squared, and a would become iota times p. So p is nothing but the value of the momentum corresponding to the energy eigenvalue E. So p is the value of the momentum. It's not an operator but a number. Similarly, for the coefficient b, we have the Schrodinger equation. By take the temporal part, the iota h bar del psi t by del t into e psi. This is the standard procedure of solving a separable partial differential equation. Okay, you can look it up on any math book. This would be del psi t by del t would give me b times it, the psi. It implies that p is minus e by h bar. Then my total wave function becomes x comma t a times to the bar h bar p x e t, and which is the solution of Schrodinger equation for free particle, and it is, if you note, is a expression for a plane wave. If you differentiate this wave function with respect to x, you would get as iota p by h of bar times the psi xt. If you note that this wave function is an eigenfunction for this operator del x, because when I apply this operator del x on this wave function, I get a complex number times the wave function again. So it is an eigenfunction of the differential operator. It means that if I take this iota by h bar on this side, that is h bar by iota del x xi x of x comma t is equal to xi x comma. This suggests us that p times that wave function for a free particle is an eigenfunction of this operator with eigenvalue p. It suggests that the momentum operator corresponding to the momentum of this particle in the x direction is this. Okay, let us denote that operator as capital P sub x, and we put a hat over it to so that it suggests to us that it is an operator. This is how we define the momentum operator's expression. So I discuss this specifically because if I introduce the expression for momentum operator while discussing the quantum physics of angular momentum, it may make you a little bit uncomfortable, as it made me while I was learning about it for the first time. That is my intention of discussing this. Let's start with the quantum physics of angular momentum. If you remember, the angular momentum in classical mechanics was given as, if L is a vector denoting the angular momentum, it is defined as r cross p, where r is the position vector of the particle and p is the linear momentum of the particle. So if you look at them at component wise, is given by this. Lz was given as x times py, y times px. In quantum mechanics, see, if you by postulate 2, this Lx, Ly and Z components are treated as dynamical variable, and we define the corresponding Hermitian operators as this. Capital Lx hat is given as capital Y hat, Pz hat, Z hat, Py hat, Ly hat, Z hat, Px hat, Z hat, Py hat. Component where x hat, y hat, z hat are the operators for x and y and z coordinates, and px hat, py hat and pz hat are the operators for linear momentum, and they take a peculiar form which I discussed just before this. Iota h bar del x. Similarly, py would be iota h bar minus iota h bar del y, and pz is minus iota h bar del. So before moving further, I want to quickly introduce you the commutator of any operators a and b. It is denoted as this, that commutator between operator a and b by and square bracket, and separate both the operators by and comma. This is defined as ab minus ba. If it is equal to 0, we say that a and b commute, and if not equal to 0, we say a and b don't commute. And some properties of this commutator is, if we have some composite operator formed by the operators a and b by multiplying or composition and its commutator with the operator c, it's same as this. If I take this a out of the commutator and take the commutator between b and c, similarly I take the commutator between a and c and write the b on the right hand side of this commutator. Another property of it is, if I have a composite operator obtained by adding these two operators a and b and take its commutator with some third operator c, is same as I take the commutator between a and c and commutator between b and c and adding both of them. And the third property is, if I have any number a or scalar a and multiply it to this operator a, and I have the composite operator obtained from adding operator b and c, is same as e comes out of the commutator bracket is same as e times a b commutator e times a c commutator. So as an example, an important example, L is the commutator between the position and the linear momentum along the same direction, and this commutator is, if I apply it to some dummy wave function xi, and note that the commutator between any two operator is again an operator. So this is an operator. Okay, so this means that this an operator operating on this vector xi. Let us apply the definition of the commutator x hat px minus px x hat applied to xi. This x hat px gets applied to this xi. This if you remember, this x hat px is minus, I have taken out this del x xi x xi, this would become plus del x, and this operator x hat is defined as multiplying the variable x to the state vector xi. Okay, this is the effect of this operator capital X hat on the state vector xi. So this would become, there would be then I to h bar can be taken outside x, this again would become del x. Note I have replaced it by this small x, the variable x, and this would be xi x plus the x times del x. This term is negative and both of this term cancel out, and this would be the remaining term. So note this operates on the state vector xi, any state which here acts as a dummy state, gives me iota h bar as a coefficient. Okay, so it means that this commutator is iota h bar. So important example of commutation, and it is true for all the three coordinates, that is this y hat py iota h bar z hat p z iota h bar, but the commutation between in a momentum operator not in the same direction as the position operator, then like for example pz is 0 on all the combination possible. Okay, let us examine the commutation of Hermitian operators L of Lx hat, Ly hat, Lz hat, that is the Hermitian operator corresponding to the components of the angular momentum Lx, small lx, Ly and Lz. This would be Lx hat, Ly hat, applying the definition of Lx, z px hat x hat pz. As I have applied the property of commutators, that I have decomposed this composite operator of this px and again applying the decomposition property of commutator y hat p z hat z hat px hat minus y p z hat x hat p z hat. So my commutator between Lx and Ly operator amounts to these four commutators. Let us denote them as A, B, C, D. So this becomes A minus B minus C plus D. So let evaluate them one by one, and I can decompose this composite operator as like this, as it is a property of commutator is p z hat z hat p px hat plus y hat z hat px hat times p z, which is y hat. Again decomposing this operator, this becomes z hat p z hat px hat p z hat z hat px hat plus z hat y hat p. Similarly, I am now decomposing this composite operator. So next step, let us first evaluate this commutator. Okay, pz hat px hat. If we apply this commutator to any dummy function x, y, z or state, this would be equal to del, approximately would be del z y, ignoring all the h bar iota factors just to simplify the calculation. This would again, okay, and you can see that I differentiate them with respect to z first or differentiate with respect to x first, it doesn't matter. Okay, so commutation would be 0, and similarly we know that commutation between any operator corresponding to any position coordinate and our momentum component operator, if they are along different directions, their commutation disappears. This is true. So this A, this thing is 0, this thing is 0, and this thing is 0. So only this term left is, you know, that this is iota h bar. And if I reverse the order of the commutation, it becomes minus of iota h bar. So this is a property of the commutator, another property. So this A becomes minus iota h bar y hat p x hat. So similarly, you can observe that this B term which we have denoted as B, this term is 0 because the z hat, py and px, all of them commute among themselves, and we would expect the commutation relating all these three operators should be 0 and this B term should vanish. And similarly, if you say a same argument for the term C, where we can see the operators involving in this commutation all commute among themselves, that is this y operator, x operator, pz operator. Okay, so only term remaining to be evaluated would be this becomes 0, this it remains to be evaluated is this term D. So let us do that. This D is this. So again, applying the properties of commutator, decomposing this composite operator first. Next would be decomposing this one, this composite operator. Again decomposing this composite operator. So this is iota h bar, this is 0, this is 0, and this is 0, and the outside of this curly bracket was p operator py. So the remaining d would become iota h bar x hat py hat. Say this would be x hat py here and y hat px over here. This is, and this nothing but the LC component. Okay, this is the result of the commutation between Lx and Ly operator. It gives us the LC operator of the angular momentum, the commutation. So if you evaluate similarly the commutation, all the possible commutation between these three operators, Ly, Lc and Lx, this would give us remaining terms would be h bar Lx and Lc hat Lx would give us h bar Ly. Easy way to remember all this is if I have a circle and denote the x and y and z components like this, then and mark the counterclockwise direction as the positive direction, then the commutation between x, Lx and Ly would give me I plus iota h bar Lc. Okay, if I reverse the order of commutation, then it would give me minus iota h bar Lc, minus iota h bar Lc. Okay, similarly, if I take the commutation between y and c, which is along the anticlockwise direction, would give me the positive iota h bar Lx. And similarly, if I take the commutation between Lc and Lx, it would give me plus iota h bar Ly. So if I take opposite order, then it would give me negative iota h bar Ly. Okay, this is then let me collect all this commutation relations between Lx, Ly and Lc. So these are the commutation relation of these operators Lx, Ly and Lc. So these three operators do not commute with each other. So considering the physical origins of this commutation relation, in quantum mechanics we can take it as a definition of some generalized angular momentum Jx, Jy and Jz, and declare that any set of three Hermitian operators which satisfy this commutation relation as angular momentum. Okay, and they also don't need to have a particular form like cross product of this vector r cross p. Okay, so in this view of things, the Lx, Ly and Lc thus become a special kind of angular momentum which has this form. Taking the commutation relation as the definition of this generalized angular momentum Jx, Jy and Jz, that is, we define Jx, Jy and Jz as those operators which has this satisfy this commutation relations. And another operator J squared of total angular momentum of the particle, okay, in the x, y and z direction, that is J is Jx I cap, Jy J cap and Jz K cap. Okay, and J square is making J dot J, which is J squared J hat squared J Z squared hat. So this is called the total angular momentum squared. So first thing is that J squared operator has non-negative eigenvalues. So let me prove that if xi is any state, then the expectation value of this J squared operator, which is equal to J squared hat xi Jy squared plus xi Jz squared. Now if I let this be Jx xi, okay, then the inner product between this phi would be xi Jx squared xi, and we know that the inner product of any vector with itself has to be non-zero quantity, non-negative quantity. Therefore this expectation value of this J squared operator has to be non-negative, and this can be said about all these remaining operators Okay, remaining terms. Therefore, my j squared has non-negative eigenvalue because it has non-negative expectation value. Number two, the thing is the state this. Okay, so by studying the eigenvalue partial differential equation written in polar coordinates of these physically inspired operators L squared and LC squared, they are not LC, they are not the operators, generalized operators. Like if in the polar coordinate this LC squared operator is given like this, and if you solve the eigenvalue equation, if this is some function of r, theta and phi, where r, theta and phi are the coordinates in the polar spherical polar coordinates, lambda, f, r, theta, phi. If you solve this eigenvalue equation and this another eigenvalue equation and involving the operator L of z, f, r, theta, phi, where LZ, sorry, I haven't defined what LZ is. LZ is defined as, then this eigenvalue equation m, let it is m r theta phi. If you solve both of this eigenvalue equation, which is then you would get, sorry, this is I denoted as mu. Okay, if you solve this, you would get mu as m h of bar, where m can take this value 0, plus minus 1, plus minus 2, plus minus 3 and so on, and lambda would come out as L into L plus 1 h bar whole square, where L can take these values m, m plus 1, m plus 2. It means that, for example, if L is 0, the possible values of L would be 0 and nothing else, and for L equal to 1, the possible values of L would be 0, minus 1 and 0, 0, minus 1 and 1. Let's continue the rest of it in the next class, in the next lecture. So bye for now, friends. See you in the next class.